Hey, hello everybody. Um, Making this video for our test one. I'm basically just going to go through the problems and sort of talk about them and write some things. And um, it's organized by timestamps. So, look in the description of the video on YouTube, and you should be able to click the timestamp to see which specific problem, if you have interest in one. So you don't want to like watch the whole thing necessarily, but you could just go here or there or whatever you're looking for. So yeah, without further ado, let's get started. Um, I'm gonna use Zoom's annotate function to talk about this here. People did pretty well on this question overall. Probably the strongest question on this entire test, determining slopes of lines, whether they're positive, negative, zero, or undefined. So generally speaking, like, as you move from left to right, if the line is going up, then the slope is positive, line's going down, slope is negative. The line is completely horizontal, the slope is zero. The line's completely vertical, slope is undefined. These two cases where they're horizontal and vertical, sort of like fringe cases, you could think, in the sense that, when the slope is horizontal, it's like all run but no rise. You're thinking about like slope is rise over run. Horizontal is all run, but it's not going up, so there's no rise. Whereas vertical is sort of the opposite. It's like all rise, but there's no run. Like it's literally going straight up. So this would be negative, positive. This would be undefined, and this slope would be zero. So let's see if I can turn off the annotate tool. Scroll. Problem two. This is about a local plant nursery in Tucson. They are selling prickly pear cacti. Imagine that. We could. There are many that do it. And you know, sort of for this problem, imagine like they have some costs of production, and the fixed costs are $5,500. Think maybe like water, supplies, soil, pots, all that. Um, or maybe not pots, because that's sort of like for the individual cacti, but like costs of starting up production sort of thing, like having the nursery in the first place and so forth. As the cost of each individual cactus plant, maybe it costs them $3 to produce. So you need to create a cost function to express their cost of growing X prickly pears. And in general, if we want to find a cost function, it's always going to be equal to the fixed cost plus the marginal cost times the number of units, or you could say fixed cost plus variable cost. So in this case, the fixed cost is $5,500, sort of like our y-intercept in this case. And then we have sort of $3 per plant. So we need to add that variable cost. It's $3 times the number of plants. See, this case, the variable cost secretly depends on the number of units you produce. Whereas this three here specifically would be the marginal cost of producing a cactus plant. Maybe now part, it's a typo, part A, two A's, should be A, B, and C. Suppose the nursery is selling some of their cacti for $30 each to Tucson Botanical Gardens. If you haven't been there, I highly recommend it. It's a beautiful place. Revenue in general, we need to find it. It's equal to price times quantity. And what does it represent? So in general, we know revenue is price times quantity. We know the price here is $30 each they're selling, and then the quantity is the number of cacti. So revenue is 30x. What does this represent? People said different things, many of which are hinting at the same exact idea. hinting and alluding, getting at. So, like, for example, you could say this revenue function represents the total cost, or I'm sorry, the total revenue earned from selling X cacti. Some people said it represents the fact that the cost or the revenue gained from selling a cactus is $30 each, sort of getting at the marginal cost, or rather the marginal revenue in this case. Sorry, I keep mixing these up in my speech, but basically, as long as you gave some sort of explanation as to what it represents, however you look at it, that was great. And there's also the question for this last part, how many cacti does the nursery need to sell to break even? The break even point is the point where you're not profiting, but you're not really losing either. You're just kind of at a net zero profit. So this occurs exactly, well, for one, when the profit's equal to zero, but more specifically when the marginal, not the marginal, when the revenue is equal to the costs. And so sort of like the costs is balancing out the money that they are making. So this nursery will just be breaking even. To do this, we would set the revenue and the cost functions equal. 5,500 plus 3x is equal to 30x. And from there, it's totally, the rest is algebra. You know, we could subtract 3x from both sides. So we get 5,500 is equal to 27x. And then we would divide both sides by 27. And we would get x is equal to 5,500 divided by 27. And you can calculate that. Something that is a nice touch is whatever number you do end up getting, you know, it's always good to put the units of cacti. It's like, it might be implied, sure, but it's always good in the context of practical problems to put sort of as much information as you can pertaining to the practical situation to accompany your mathematical findings. That's pretty much all I have to say about this problem. So I'm going to clear these and scroll to the next page. Okay. Problem 3, suppose the marginal cost of producing an iPhone is $270. I looked this up when creating this question. This is somewhat in the ballpark of the actual range. What could this mean to Apple, who is producing the iPhones? Sort of these options. The cost of producing the first iPhone ever made. That might be more like, if you were to look at the cost function, that might be something like C of 1, depending on how you interpret it. But that would still include the fixed costs of production. So it's not quite the marginal cost, it's too much. Same with part B that says $270 is the cost of producing thousands of iPhones. That's more like total cost of a certain number of iPhones. If we look at part D that says the cost of producing 0 iPhones, that straight up would be your fixed costs. Like you're not producing any iPhones, but you still might have the costs to start up production. The actual interpretation of marginal cost is always the cost of producing one more or one additional of whatever you're producing. In this case, the cost of producing one additional iPhone. That would be the marginal cost of producing an iPhone. That $270 is the cost of producing one additional iPhone. So Apple's already got all their stuff set up, and now they're just pumping out iPhones, and every iPhone they pump out, basically, it costs them $270. Okay. I'm going to clear that just so I can scroll down a bit. This problem 4 definitely wanted to talk about, because for one, it's multiple choice, but I did grade this with sort of as much partial credit as possible in case people didn't select like the right answer. Of course, if you selected the right answer to honor the multiple choice format, I just gave full points regardless of work shown or not. For starters, the answer is somewhat like this. Or rather, I should just say like these are the correct answers. But why? But why? What's the situation? A charter boat is charging a fare of $120 per person. You imagine a boat, and they're like letting people on. They're like, pay up, $120 plus some extra, depending on how many seats that they don't have filled. Imagine like these airlines or something. Like they're always trying to fill up their flights to get sort of the most efficient use of the fuel and the transportation time. Um, Sometimes an airline will straight up cancel a flight when not enough people are booked, which is kind of annoying. But I mean, from a business perspective, I suppose you could see why they do it. Maybe that would be them operating at a loss. So that's sort of the rationale for this sort of setup, that plus three additional dollars for each unsold seat on the boat. And they have a capacity of 80 passengers total. And they say let X represent the number of unsold seats. So not the total number of seats, but the number of unsold seats. They want us to find the total revenue received for the boat. Now, I mean, there's sort of a lot here, but what we can do to sort of get an initial handle on it is look at what they're asking for. Total revenue, sure. What do we know about revenue? Revenue is always equal to price times quantity, in the sense like how much you're selling something for times how many you sold. Price times quantity is always how we can start to sort of find our revenue. In a specific situation, these might just be numbers, but in this case, basically the price and the quantity both depend on how many seats are filled. Because they say let X represent the number of unsold seats. We want to sort of find an expression here in terms of X. Quantity sold, they're selling seats. So the quantity is simply the number of seats that they sell. We want to get that in terms of X, which is the number of seats that they didn't sell. So it's kind of like a little topsy-turvy. If they have a capacity of 80, and we subtract off the number of seats that they did not sell, this 80 minus X here is the number of seats that they did sell. So that's our quantity. Well, as for price, certainly we can like approach this many different ways. Like how much is each person getting charged based on the number of unsold seats? They sort of tell us it starts at 120, regardless, that's our base price. So we're going to sort of have a baseline of 120, but plus a bit extra. How much extra? Plus $3 extra for each unsold seat. We know $3 times the number of unsold seats is going to account for that bit of information. This is sort of like more of a talking through it type of way, which certainly is possible. In the moment, especially in like a time test setting, it can be useful sometimes to do things more procedurally. If you're like not sure and you just want something that is going to work. So like another option for either of these price or the quantities is to sort of like create, 2 points like X comma Y. And you can certainly use those points if it's going to be a linear function to find the equation of the line. So like just for example, we know that let's at X represents the number of unsold seats. If there are 0 unsold seats, that's when it's going to be the cheapest for everybody. That's when they're going to charge $120 per person. Whereas, maybe on the other end of the spectrum, if there were 80 unsold seats, I guess no one would be charged, right? But it would be a lot higher. But in general, it's going to go up. So imagine if there was just 1 unsold seat, there were 79 people on the boat. that had seats. They say that they're all going to get charged $120 per person plus, $3 for each unsold seat. There's just one unsold seat. So like, for instance, if you wanted to find the price function as a function of X, it would be linear and you could use these 2 points to find it. If you weren't like into talking through it or like coming up with it sort of more like I showed before. The same applies to the quantity. I'm not sure like if anyone thought of it like that, but if you want to see more about that, you can certainly message me and we can talk about that further individually. As for the maximum revenue, I mean, once we have the function here, 120 plus 3x times 80 minus x, we see this, if we were to multiply this all out, it would be like something with an x squared. Actually, it would be like the leading coefficient would be -3. So it'd be like -3x squared plus ... other things. Why do I say that? It tells us that the parabola is somehow going to open downwards like this. And so if we want to find the maximum revenue, really we need to find the vertex of this parabola. So one option is straight up to just type this into our calculator and graph it and use the functions on the calculator like the maximum to find where there is a maximum, and it would tell us. Another option is if you have a quadratic with the form ax squared plus bx plus c, you can always find this highest or lowest point, the vertex, sort of, depending on whether it opens up or down. It's always, regardless, going to be negative b over 2a. So like if we wanted to approach it like this, we could FOIL this out 120 plus 3x times the 80 minus x. And, we could find negative b over 2a. That would tell us like the x value of where it occurs, or like rather how many seats. If we wanted to find the price, we could plug the vertex back in to the parabola, to the quadratic function. And in the end, I think the revenue ended up being maximized somewhere around like 10,800. There are yet more ways to do this problem. Like later, we're going to see a way to do this problem by taking a derivative, and setting the derivative equal to 0. So maybe you even approached it like that if you happen to already have that knowledge. Yeah, if you want to discuss more about this problem or any other problem here beyond what I'm talking about, I mean, we could always talk about test one-on-one. Going to scroll to a future problem. Let's see. This was the question that was sort of scrapped from the exam, but that I still gave everyone 2 points for. So the test is out of 50, and that does not include this question. However, I added 2 points to the numerator out of 50, even though this question does not factor into that denominator out of 50. The vertical asymptotes of this function, x1 divided by x squared minus 25, they can be found by setting the denominator here equal to 0 and solving for x. Because asymptotes, vertical asymptotes, always occur when we are dividing by 0. So x squared minus 25 equals 0. You could factor this maybe as x minus 5 times x plus 5 and set those each individually equal to 0. We would get x is equal to -5 and +5. And you could also do x squared equals 25, take a square root. When you take a square root, you sort of have to add in a plus or minus because it could have been negative, who knows, to start with, or positive. -5 squared is the same as 25, is the same as 5 squared. The reason this question is flawed, in my opinion, is because it should also say x is not equal to -5 here. This is really a statement about the domain of the function excluding 5 and -5, and I just forgot to put both. So I'm sorry about that. Horizontal asymptotes of this function. We can always find the horizontal asymptotes of a rational function by comparing the degree of the numerator to the degree of the denominator. If they're the same, which is not the case here because the degree on top is 0 and the degree in the bottom is 2, being quadratic. The asymptote would be at the ratio of the leading coefficients. Here, the degree on the denominator is strictly bigger. In that case, it's always going to be an asymptote at 0. The question then is x equals 0 or y equals 0. And really just which of these equations gives a horizontal line. I mean, the answer is y equals 0. And just to sort of recap the reasoning on this, if you imagine a horizontal line, what all of the points on this line have in common is that they have the same height, like on the y-axis. They all have the same y value. Technically, I should draw it coinciding at y equals 0, but I'm just talking about equations of horizontal and vertical lines now in general. I mean, the other way around, if you have a vertical line, what all the points on this line have in common, they're going up and down, sure, but they're all positioned at x equals a particular values. They all have like 5 comma whatever number. So that's all I have to say about those. There's also this question about supply and demand, finding equilibrium quantity and equilibrium price. Intuitively speaking, equilibrium occurs when supply is equal to demand. So we can start here by setting them equal to each other, even if I sort of don't know about the units of the problem. I mean, we can look at that later. We are going to, and we should. So like 0.008x is equal to 500 minus 0.001x. And then, we could add that 0.001 to both sides. We get 0.009x equals 500. What does that tell us? It says x equal to 500 divided by 0.009. And what I saw people get for this was this is about equal to 55, 5, 5, 5-ish. X here is the quantity of PS5s produced and sold in thousands. So the meaning of this is really like this is a number that means thousands of PS5. So it's really like we're adding 3 zeros to this. 55 million-ish, 555,000 PS5s is like the equilibrium quantity. And if we want the equilibrium price, what we can do is we can plug this back in to either the supply or the demand, whichever you prefer. But make sure to plug in what you found for X, not with the thousands. And so if we were to plug this in, it would tell us that the price, the equilibrium price, is about $444. I wasn't crazy about like rounding or anything like that. If it was sort of in the right ballpark, that was great. Mostly what I was looking for is like consideration of the thousands and of course knowing like how to find the equilibrium point in the first place and like making sure not to forget about the price because both of them are asked for. So if you showed work or you explained how you knew and you did all of these things, you got full credit. Pretty much all I have to say about that, other than the fact that this problem is realistic. I created it using somewhat real data that I looked up online. So problem 7, suppose the restaurant Taqueria El Pueblito can model their total costs in dollars of making and serving X burritos by this cost function. They say C of X equals 1375 plus 2.50X. What's the average cost of making and serving X burritos? Something to know, first of all, is that the average cost in general of however many things you make is always going to be like the total cost divided by the number of units produced. In this case, we're making burritos, right? So it's like the total cost of however many burritos divided by that number of burritos. Um, Sometimes this is written with a bar over it. Like I've seen this pop up in our study guides. So the average cost is going to be if we took the total cost, divided it by the number of burritos, which is simply X. Imagine like, depending on how many burritos you make, the average cost is going to be different. Like if you're just making one burrito, it's going to be pretty high. But as you start to make more and more burritos, the average cost starts to kind of drop off. See, like we're dividing by X. And something that is interesting for calculus purposes, even though it wasn't sort of asked for in this question, is that the limit as X approaches infinity of the average cost is going to be equal to 2.50, which is the same as the marginal cost of producing and making and serving a burrito, really. If you just put the average cost function, you got full credit. I mean, a lot of this I think is just like knowing what is the average cost, how is that calculated, and like making it in terms of X. That's all I have to say about this question. Other than that, it is not based on real world data in this case. I did not ask the Taqueria El Pulido, but you could go there and it's very good. Highly recommend. As for problem 8, this is a true false type question. Determine whether the following statements are true or false based on this graph right here. So let's see. Limit as x approaches 1 of f of x is equal to 1. Is that true or false? Here's x equals to 1. And as we see, we do have a hole here. So the function itself does not have a value at x equals 1. But, you know, all around it, it sort of has the function is there and it is kind of going towards this hole. So we can still say, even though the function doesn't exist there, we can say that as we approach 1 from either side, as from our input, the value of the function does indeed go towards 1. Even though it doesn't actually exist there, the limit as x approaches 1 of f of x is still equal to 1. So it doesn't need to exist to have the limit there. True or false, limit as x approaches 3 of f of x is equal to 4. This one would be false because we see at first, okay, if we look at 3, there's a jump. And looks like from this side, as we approach 3, it's going towards 3, the value. But from this side, as we approach 3, it's going towards a different value. It's going towards 4. So we could say that the limit from the right side is 3. Say that the limit from the left side is 4. But because they're different and they don't match up, like the limit itself as x approaches 3 does not exist. Even though both of the one-sided limits exist, they have to be equal for the total limit to exist, or for the sort of the two-sided limit, as it's sometimes called. Whereas, you know, the limit as x approaches 3 minus, that's saying from the left, the limit as x approaches 3 from the left of f of x is equal to 4. Oh, yes, it is, because as we see here, sort of as we go from the left of 3, the value of the function is approaching 4. This is true. And true or false, f of 3 is equal to 3. As we can see, there's a hole here and there's a dot here. Let me clean this up a little bit. There is a dot here. That means this is what the function is equal to. So this tells us that actually f of 3 is equal to 4. So f of 3 is not equal to 3. This is false. If it was the other way around and it was this dot that was filled in and this was an open circle, then it would be true. But in this case, it's the other way around. It's false. That's about all I have to say here. Sort of practice with making distinctions between limits of functions from either side and values of the function. Okay, problem 9. Suppose we have a table of values. What is the limit as x approaches 0 of f of x? We have this table. It looks like that. Okay, at x equals 0, the value of the function is 322. That tells us that f of 0 equals 322. It doesn't necessarily tell us that the limit as x approaches 0 is that. And in fact, it looks like as we sort of come at it from either side, this from the right, sort of as we get closer and closer to 0 for our input, the value of the function is just going straight up, like really high, like 10, 100, 1,000, 10,000. It seems like it's going up and up and up, higher and higher up towards infinity. Whereas right here, it looks like it's going sort of more and more and more down, like -10, -100, -1,000, -10,000. It's going so down. The graph would look maybe something like this, with like a little hole here, or rather a closed circle, not a hole, at 322. A little dot here at 322 for the actual value of the function. But it's not the same as the limit. It looks like the limit from the right is, if it could be anything, it would be positive infinity. Whereas the limit from the left, if it could be anything, it would be negative infinity. But they don't match up because they're going up towards different directions. So the limit doesn't exist because it doesn't match what it's going towards from both sides. Define the function here, this is problem 10 now, by x squared plus x plus 1. We are asked, what is the limit as x approaches 0 of f of x? One thing we can always try is straight up plugging it in. When this is a continuous function that we have the limit of a continuous function at a point is the same as the value of the function at that point. So like in this particular case, we can say that the limit of x approaches 0 of f of x, it is indeed equal to f of 0 because f is continuous. All polynomials are continuous. Quadratic function, example of a polynomial. If the function was like we had above on the graph on the previous page, you can see that that's not the case. Or even right here, the limit is not the value of the function at that point. But here, we would just simply plug in 0. It would get rid of these terms. The limit would be equal to 1. So f of 0 is equal to 1. And that would be the limit in this case. You can find it by plugging in 0. Okay. All I have to say about these, I'm going to keep going. Okay. Which of the following graphs could possibly be the graph of minus x cubed plus x squared plus x? For one, when I wrote this question, I was kind of thinking like, well, maybe people could appeal to their knowledge of end behavior and of leading coefficients. Like this being a minus sign tells us that it sort of opens either up or down in a certain way. Or like this x cubed, the degree being 3 tells us that it's not going to be like a parabola. It's going to be more kind of like a cactus, really. You could find parabolic looking cactuses too. Maybe I'll show you in class. So the fact that it's x cubed immediately can tell us that it's not these first two. That would be more of an even degree, like x to the fourth or x squared. But it's got to be one of these. And the fact that it's a minus sign tells us, well, this would be more like the graph of x cubed. This would be more like negative x cubed. The fact that it's sort of opening this way rather than this way, um, or rather the fact that there is a minus sign tells us that it's opening more like this rather than like this as a general shape. So it's going to be this. Alternatively, and I didn't really anticipate this, but it's perfectly good. You can graph it on your calculator to put a picture in your head rather than sort of think about it like this. But I think people thought about it in both ways, which is great. So, let's talk more about this. Problem 12. Consider the function f of x is x squared minus 4, all divided by x plus 2. And we are asked to evaluate the limit as x approaches negative 2 of this function. As you can see, sort of to start, I'd always kind of recommend this. If you plug in the limit that we're trying to calculate, or like the value that we're approaching for our inputs as an input, we can see what happens. So like here, if we plug in negative 2, f of negative 2, what happens? We get negative 2 squared minus 4 divided by negative 2 plus 2. What's that? Well, negative 2 squared, that's positive 4. So we get 4 minus 4 over minus 2 plus 2. I guess I'm leaving that, but as you can see, it becomes 0 over 0. What this could mean is a couple of things. It means maybe the limit exists, maybe it doesn't. But either way, we need to do more to find out whether it does or it doesn't, and or what it is. So basically, one option is that we could graph this function. And if you type this function into your calculator, what you will find is that it kind of looks linear. That was not the greatest of my lines. Just have to manage, act like this is a straight line. And what you should find on your calculator is a line that looks kind of like this. It probably won't do a good job, but technically speaking, the graph would have a hole at negative 2 because the function is not defined. But everywhere else, the function would simply look linear. And we can take the limit as x approaches negative 2 of that and see what it comes out to. And what does it come out to? I mean, I don't have the function exactly graphed, but I mean, here's another way. Like if you want to look at it as factored form, factor that x squared minus 4 up top into this difference of squares. So x minus 2 times x plus 2. And then we can cancel out this x plus 2 factor, leaving us only with the x minus 2. So, I mean, you see, if we were to graph this like on an actual calculator, this value here that has the hole, it would be sort of like at minus 4, it would be minus 2. So the limit as x approaches minus 2 of f of x, this is a vertical equal sign. It's the same as the limit as x approaches minus 2 of x minus 2, because this is equal to the function everywhere except at this one little hole. But that's okay for limits because limits don't care what happens at a point. They care what happens around. So for here, we can see straight up, if we plug it in, the minus 2 for x, we get minus 2 is minus 4. And so like that would be the limit. This limit is equal to -4. Yet another method to look at this is if you didn't want to look at it like factoring, you didn't want to look at it like graphs, make a table of values centered at -2, like -2.001. I think I want that on the other side, but -2.01, say, -2 point, -1.99. You could make it go even closer. Like it could be 0.00001, -1.99999. If you were to do this table, and make sure like you're careful with putting your negative numbers getting squared in parentheses so that the value isn't off. Basically calculate this correctly, you'll see that at this particular value, -2, it doesn't exist, but the function's basically getting closer and closer to 4 on both sides. So like you could fill in a table like this and find the limit like that. And this is always true. Like you can always use a table to find limits. If you have like a function with a formula like this. So, problem 13. Okay. Suppose we know, where'd my annotate tool go? Suppose we know that the limit as x approaches infinity of f of x is equal to 8, and that the limit as x approaches -infinity of f of x is also equal to 8. What can we say about the asymptotes of f of x? I wanted you to explain your thinking. What I was hoping for, based on like what we've emphasized in like class and on some of the online notes, is like the connection to be sort of found or remembered about the connection between limits at infinity and horizontal asymptotes. So like anytime you see a limit at infinity or negative infinity, either or, that always tells you info about a horizontal asymptote of the function. So like when it's equal to 8 like this. Like if I were to draw a graph, I have no idea what this function is, right? It could be anything. But what it's basically telling us is that if this is the line y is equal to 8, that's this dotted line. Whatever this function does, who knows what it does? Maybe it does some crazy thing in the middle here. It's even discontinuous. And then it's like, I'm going like this. But then maybe it's kind of levels out. You can cross a horizontal asymptote. It happens oftentimes that the function doesn't, but you could. A vertical asymptote, though, is really what is never going to be crossed. It could even be the case that this function has a vertical asymptote. I mean, maybe if I draw it slightly differently, I could draw it, there's like a vertical asymptote right here, and it's going down. Let me draw this a bit better, carefully. Maybe the function looks something like this, and it's got a vertical asymptote in the middle. It may or may not. We actually don't know whether it does. All we can say is about the horizontal asymptotes. It may or may not have vertical asymptotes. So, I mean, if you said anything about a horizontal asymptote, basically that was like full credit for this question. And if you said something about an asymptote, but it wasn't horizontal, that was like partial credit. It's still, yeah, it's got to be like sort of one or the other, probably. Maybe like a meta approach to this problem. But yeah, and the horizontal asymptote is always at like y equals 8, as opposed not to like x equals 8. That would be a vertical asymptote if that was such a thing here. Okay. So that's all I have to say about that. And scroll down a little bit. All right. Problem 14. I'm gonna like zoom in on this. This is a classic problem in intro calculus classes. It says we have a function, okay, f of x is x squared plus 2. Compute f of x plus h minus f of x all over h for h is not equal to 0. If h was not equal to, or if h was 0, it would be 0/0, and it would not be um, sort of anything in particular. It would be indeterminate, as they say, for 0/0. But for h not equal to 0, we can see what this is. Um, so f of x plus h, sort of break this into pieces. What is that? We're taking x plus h, and we're plugging it in for x here. So it becomes x plus h all squared plus 2. And we can like FOIL that out. We get x squared plus h squared plus 2. And don't forget in the middle, there's a plus 2xh that comes from the foiling from when the x's and the h's distribute to each other. So yeah, it doesn't look like we have any like terms here. We know what f of x is. It is simply x squared plus 2. I'm going to line these up, vertically speaking. And just because I want to show about the cancellations. If we were to subtract these off, sort of like this, what we would see is that the x squareds cancel out and the 2's cancel out. So this tells us that f of x plus h minus f of x is equal to just this stuff that's left over. It's this 2xh plus h squared. And we're almost done. We still have to over h, right? So all of this over h. And since h is not equal to 0, we can cancel out some h's. However you want to think of it, I mean, you might like just cross out things like this and put it to a 1. You might also think like, oh, I can factor out an h out of the top like this. That's all over h. And this is kind of going off the screen. These h's like cancel, leaving us just with this. That is the answer, 2x plus h. And I mean, that would be the computation. The meaning of this computation and like its importance to our class is that this is really the difference quotient, the definition of the derivative. And so if we were to take the limit as h approaches 0 of this whole thing, which really ends up turning out to be the limit as h approaches 0 of 2x plus h, as you see, we just plug in h equals 0, and it gives us 2x. The meaning of this is that f prime of x is equal to 2x. This is the same as the derivative of f of x with respect to x. This calculation shows basically if we were to take the limit as h approaches 0, the derivative of this function here is simply 2x. Okay. That's all I have to say about that. Average rate of change of a function. In this case, they give us sort of a function, 9x cubed plus x squared plus 3. And we are to find the average rate of change of this function over the interval from 0 to 1. Always what this means is, if we were to graph this function, who knows exactly what it looks like. We could graph it, but it looks something like this. And maybe here's the point 0, 3. And maybe here's the point. It looks like it should be going up. So this function isn't quite drawn to scale. But like, imagine if it was something more like this. Can I erase a little bit? Yeah, okay. Might look something like this. And at the point 1, maybe there's another point that's like, it's 1 comma, what is it if we plug in 1 to this function? That's how we would find the value. F of 1 is equal to 9 times 1 cubed plus 1 squared plus 3. Of course, 1 cubed or 1 to the power of anything is still 1. So it's going to be 9 plus 1 plus 3 for a total of 13. Yeah. And so we have 2 points on the function. To find the average rate of change over this interval, what we really want to know is if we were to draw a line between these 2 points, what would be the slope? And we know how to find slope. It's rise over run. So, we could do either order here, but like y2 minus y1 over x2 minus x1 would come out to like 10 divided by 1, which is 10. That would be the average rate of change of this function over. All right, very last question on this test. It says this graph shows the tangent line to f of x is 7x cubed plus 7 at the point 5 comma 882 pictured here. And you see the graph, this is the function, and this tangent line sort of touches it at this one point. And suppose the equation of the tangent line graphed above, okay, we have the equation is 525x minus 1743, that's y equals. So when we're asked, what's the instantaneous rate of change at x equals 5 of y equals f of x? What is the instantaneous rate of change of this function at x equals 5? It is simply, and this is always the case, the instantaneous rate of change at a point is the slope of the tangent line at that point. So, one could simply see slope of the tangent line is 525. The instantaneous rate of change is 525. What I saw, like some people may not have made this connection immediately and sort of fell back on like the more familiar maybe like definition of the derivative type of thing. And I saw people even use like the power rule to take derivatives here. You certainly can find like, the limit as x approaches, not x, I'm sorry, h, as h approaches 0 of f of, well, we wanted at x equals 5, right? So we could find like 5 plus h minus f of 5 all over h. If you did this whole calculation out, it would be a bit much, like in terms of like being a bit tedious, because of the x cubed, and you have to like FOIL stuff out. You would find that it's equal to 525. On the other hand, if you decided to use the power rule for like 7x cubed plus 7, yeah, you would have found like 3 times 7, you'd have found 21x squared is the derivative, yes. F prime of x is equal to 21x squared. And yeah, if you plug in x is equal to 5 here, you'll get the same 525. So all of these ways are valid and valuable as well. I would say definitely the fastest way here is to sort of rely on the given information that the slope of the tangent line is this, and no calculation is needed. But certainly these are both equally valid ways to look at it. So yeah, that's all I have to say about the test in terms of like how to do these sorts of problems, but we could always talk more about this individually or as a class if everyone had very similar questions. But overall, people did very well. Great job. And thank you. I hope you got something good out of this video. And if you have any questions about anything in it, please send me a message or tell me in class and we can talk about it more. Thanks.